Dear students, in today's video we are going to discuss the important application of Gauss law, that is to find the electric field intensity due to a uniformly charged spherical shell. So here we have a spherical shell which is uniformly charged. The positive charge is present on the surface of the spherical shell. This is the way the question will appear in the exam, that to apply the Gauss theorem for the spherical shell and show that the electric field inside the shell is 0. If you calculate E inside the shell, it is equal to 0. Second, the electric field is maximum at the surface of the shell. If you have observation point on the surface of the shell, then the electric field will be maximum, and if the observation point is outside the shell, somewhere at this distance or maybe at this distance, then the electric field outside the shell varies inversely with the distance of the observation point. If you will move the observation point away from the spherical shell, the magnitude of the electric field will decrease. Let us discuss what is the direction of the electric field produced due to this spherical shell. As the spherical shell is positively charged, the electric field lines are directed radially outward. So the electric field lines are outward from the spherical shell. First of all, we choose a point P which lies outside the spherical shell. We know that to apply Gauss theorem, we need a Gaussian surface. So we choose a Gaussian surface with radius r. This Gaussian surface is concentric with the spherical shell. The center of the Gaussian sphere and the spherical shell is same at this point. Capital R represents the radius of the spherical shell, and this small r represents the radius of the Gaussian surface which passes through the point P. We choose a area element ds1 such that the area vector ds1 vector can be written as ds1 dot n cap. N cap is the normal to ds1. Then we know that n cap has this direction, the electric field is radially outward. So n cap and the electric field E are in same direction. Then we apply the Gauss law. Gauss law states that the total electric flux is equal to surface integral of the dot product of electric field and the area vector, and it is equal to the total charge present inside the closed surface divided by epsilon naught. We solve the dot product by using a dot vector dot b vector is equal to ab cos theta. Our theta is equal to 0 degree. So theta angle is 0 as n cap and electric field E are parallel to each other. So cos 0 degree is 1. So we have EDS1. Electric field is uniform as the spherical shell is uniformly charged. It can be taken out of the integration, and the integration is left over ds1 only. So this is ds1. If you want to calculate the entire area, it will be equal to the area of sphere, that is 4 pi r square. Qn is the amount of charge, and we know that the spherical shell has total charge capital Q, so we replace Qn with capital Q. So this is the amount of electric field which will be experienced at point P. As we can see that the electric field is decreasing as the distance of observation point from the spherical shell is increases. If you choose sigma to be surface charge density, then sigma will be ratio of the charge on the spherical shell divided by the area of the spherical shell. So area of the spherical shell is 4 pi capital R square, because capital R represents the radius of the spherical shell. So Q can be written as sigma multiplied with area. So it is sigma, the surface charge density, multiplied with 4 pi r square. So this q has value 4 pi r square into sigma. Then we choose the point q, which lies on the surface of the spherical shell. So we have this point q. The things remain same. We choose the area element ds2, n cap, and electric field E has same direction. So when we apply Gauss law, then theta is equal to 0 degree and the integral is E ds2. We take E common and the integration is left over ds2 only. On another side, the q in will be replaced by capital Q, the total charge on the spherical shell. On rearranging the terms, we get this expression, right? Here we substitute the value of capital Q, which we just calculated over here, that it is equal to 4 pi r square into sigma. When you substitute this value, 4 pi and 4 pi will cancel out, r square and r square will cancel out. You will be left with sigma by epsilon naught only. This is the amount of electric field experienced by the charged particle when it is present on the surface of the spherical shell. Now let us calculate the electric field inside the shell. We choose a point L which is present inside the spherical shell. To apply the Gauss theorem, we choose a Gaussian surface with radius r prime which is passing through this point L. R prime is less than r. Capital R is the radius of the spherical shell. As the point L is present inside the shell, the Gaussian surface radius r prime is less than r. We know that no charge is present inside the spherical shell. The entire charge is present on the surface of the spherical shell. So, the total charge Q in for this Gaussian surface is equal to 0. Application of the Gauss law, the total electric flux can be calculated by knowing surface integral of E vector dot area element vector is equal to Q in by epsilon naught. If Q in is 0, the charge inside the spherical surface is 0, then the total electric field is equal to 0 inside the shell. On the basis of the entire information, we can write that E inside is 0, E on the surface is 1 upon 4 pi epsilon naught Q by r square, where this capital R represents the radius of the spherical shell. Then E outside is equal to 1 upon 4 pi epsilon naught times Q, the total charge on the spherical shell, divided by r square, small r square. This small r square represents the radius of the Gaussian surface which passes through the point of observation. So, we try to plot a graph. One side we have taken the electric field, on another side we have taken the distance r. So this is our spherical shell. When you are inside the spherical shell, the electric field is 0. As you move on the surface of the spherical shell, the electric field has maximum value, and this value is equal to E is equal to 1 by 4 pi epsilon naught Q by r square. As the observation point moves away from the surface of the spherical shell, the electric field intensity decreases, right? Higher the value of r, higher is the distance from the surface of the spherical shell, lesser is the value of electric field intensity. This is all about the application of Gauss law to calculate the electric field due to a spherical shell at a point inside the shell, at a point on the surface of the shell, and at a point outside the shell. Thank you.